Welcome everybody to CCNP Enterprise Infrastructure. In this section, we're going to be talking about campus network architecture. My name is Brian McGann. I'm a Cisco certified design expert, as well as a CCIE in routing and switching, security, service provider, and data center. For any questions that you have about this course, you can feel free to email me, bmcgann@ini.com. Follow me on Twitter @BrianMcGann or on linkedin.com/in/bmcgann. Now in this section, we're mainly going to be focusing on the hierarchical LAN design models. So building hierarchy for the LAN is going to divide the network architecture into modular layers, where each layer is going to be implementing a specific function. The goal of this is to make the network easier to scale and to provide fault isolation and to ease troubleshooting as things go wrong in the network. Now specifically, the hierarchical LAN design model breaks the network into three building blocks, which we call the access layer, the distribution layer, and the core layer. The access layer is where our endpoints attach, like PCs and IP phones or IP cameras. The distribution layer is going to be the aggregation point for the access layer, and it's going to be the services boundary between the access layer and the core. The core layer is going to provide connectivity between the distribution blocks and provide high-speed switching of the traffic between the distribution blocks. So here we have a visual representation of what the three-tier campus design network looks like, where we have the access layer multi-homed up to the distribution layer. The idea being that if one of the distribution switches fails, we still have an alternate link to forward traffic up towards the distribution block. And likewise, we have multi-home connectivity from the distribution up to the core block. In case one of the core switches or the distribution switches fail, we have redundancy in terms of the nodes, and we also have redundancy in terms of the links. Now, in terms of scaling the network with blocks, the number of layers that we're actually going to use is going to depend on the network deployment characteristics. So a single building, for example, might only require distribution and access layers, which would be called a tier 2 design, or in other words, a collapsed core. But as the network begins to grow, the core layer is used to scale out the network, where scale out means that we're adding more boxes horizontally, as opposed to scale up, which means we're adding more powerful boxes to scale the network, to scale an individual box vertically. Okay, now the first of these layers, the access layer, is also known as the network edge. So as I mentioned, this is where our end devices are attaching. So for example, PCs, phones, wireless access points, printers, IP cameras, any device that's running the IP protocol is going to be attached at the access layer. Okay, this provides high bandwidth access to both wired and wireless access points. And it's also going to be our first stop for our first hop, I should say, for quality of service trust points. Okay, the access layer generally can be logically segmented using VLANs, where we have different logical networks for performance management and security. And communication between the access blocks is going to occur through the distribution blocks. So from a physical point of view, the access switches are connected north-south to the distribution, and the access switches are not connected east-west to each other. So if we go back to our diagram, we notice that the access layer does not have a connection between the two access switches. We would have to go up to the distribution block in order to go between these two different PCs that are connected between two different access switches. Okay, next we have the distribution layer, which is also known as the aggregation block. And this is going to be aggregating our access switches in the building or the campus, which is going to do a couple things for us. First and foremost, it's going to reduce the number of cable runs, and we're not going to have to daisy chain the access switches together. Okay, under most normal circumstances, the distribution block is also going to be the layer 2 to layer 3 boundary, where we're going to be running layer 2 spanning tree down to the access layer, and we're going to be running layer 3 routing up to the core layer. Okay, this is also the logical place where we would do IP summarization. So we would take the IP subnets of the access layer, and we would summarize those as we're advertising them northbound or upstream to the core. Okay, the distribution switches should be deployed in pairs for redundancy. So again, we have not only link redundancy in terms of how we're physically interconnecting the switches, but we also have node redundancy, that if we lose an individual switch, that we're able to keep forwarding traffic around that failed node. Okay, this is also where we would see the feature called stateful switchover, or SSO, in chassis-based solutions, where we have multiple supervisors or multiple CPUs that are running the chassis-based switch. And if one of the CPUs dies, we're able to switch over to the other one in a stateful manner, meaning that we're able to continue to forward traffic without any loss in the data plane. Okay, the distribution switches themselves will interconnect to each other with either layer 2 links or layer 3 links, depending on our particular design. Okay, and last but not least, we have the core layer. So the core layer is the backbone, and it's the aggregation point for multiple networks. It's going to provide high-speed layer 3 connectivity between the distribution blocks and the WAN, where the WAN is where we would have potentially private access to multiple remote sites, or where we're connecting to cloud providers like Amazon AWS, versus the internet where we're just doing regular internet connectivity, or where our VPN users are coming in from our remote sites, whether this be remote offices or end users at their homes that are connecting over VPN connectivity. We also have the data center connected here in the core layer, so any type of like e-commerce transactions that we're doing or any type of big data is going to be maintained in the data center. And then the network services layer as well, where we're doing things like authentication and other services like load balancing would happen in the network services layer. Okay, the other goal of this is to reduce the cabling needs from a full mesh of connectivity, which can be represented by the formula n times n minus 1 over 2 number of links that we would be required to connect the distribution blocks to n number of links for the distribution switches. Okay, in terms of different network design options, multiple options are going to be available for building the campus network depending on the scale. So we could have a two-tier design where we're collapsing the core and the distribution together in a single layer. We could have the three-tier design where we have the core, distribution, and access. And in either of these solutions, we could either be running layer 2 down to the access layer, where we're running spanning tree from the access layer up to distribution, or we could be doing layer 3 access, where we're doing layer 3 routing from the access layer to the distribution layer. Okay, we'll also talk about the simplified campus design, where we're using multiple chassis that are going to be clustered together, like in a virtual switching system or in Stackwise, that is going to simplify the overall design in terms of the spanning tree and in terms of the layer 2 connectivity. Okay, the first of these, the two-tier design or the collapsed core, might be useful for smaller networks that don't require a core layer for interconnectivity. So this is going to be a cost savings that we don't need additional devices in the core layer in order to connect the devices in the network. So the two-tier design is going to use just an access layer and a distribution layer. And in this case, the distribution layer is also acting as the core. So we're connecting from the distribution southbound to the access layer switches, and we're connecting northbound to our services like the WAN, the server farm, the internet, and our network services. Okay, as the network starts to grow though, larger networks are going to require a core network for interconnectivity between the distribution blocks. So this might be a function of the cabling requirements between buildings, where it might be administratively prohibitive to run the amount of fibers that we need to connect the distribution blocks directly together. Or it might be a function of the northbound connectivity requirements, meaning the WAN or the internet. As we start to overload the individual distribution block, we might need to separate these into the core connectivity of the core block. Okay, the idea is that the core layer is going to be comprised of high-speed switches running layer 3 routing, and the core switches are going to connect to pairs of distribution switches using a layer 3 protocol such as OSPF or EIGRP. But in any case, we're always going to be deploying the core layer, the distribution layer in pairs, so that if one of the switches goes down, we're able to continue forwarding our traffic in the data plane around the failure that is introduced into the network. Okay, in the traditional network design, we use layer 2 access layer and a layer 3 distribution layer, where the distribution layer is going to be hosting the default gateways for our end stations. Okay, the potential problem with this is that loops in the layer 2 network are going to cause spanning tree protocol to block links, and redundant uplinks from the access layer to the distribution layer are going to remain unutilized. Okay, the ideal recommendation would be to limit VLANs to an individual access switch, so that loops could be removed by using layer 3 connectivity between the distribution switches instead of layer 2. but this might not be possible if VLAN services need to span between multiple access switches. Okay, with layer 2 access, we're typically running what's called a first hop redundancy protocol in the distribution switches, because these are going to be the default gateways for our end hosts. Okay, so a first hop redundancy protocol should be run between the distribution switches to provide default gateway redundancy. And we have one of three protocols we could use, either the hot standby router protocol, or HSRP, the virtual router redundancy protocol, or VRRP, or the gateway load balancing protocol, or GLBP. Okay, the first of these, the hot standby router protocol, or HSRP, provides active standby redundancy for the default gateways, where the switches are going to agree on a virtual IP address and a virtual MAC address of the default gateway. Okay, the end stations are then going to send an address resolution protocol request or an ARP request for the default gateway, and they're going to be returned back with the virtual MAC address of the HSRP group. Now, the potential limitation for this is that only one of the distribution switches is going to be the active forwarder. So one switch is going to be the active gateway, one is going to be the standby gateway, and the result of this is that the uplinks from the access layer to the distribution layer might be underutilized. Okay, technically we could do load balancing by running multiple copies of HSRP. So for example, we could use one HSRP group for the even VLANs, we could use another HSRP group for the odd number VLANs, but unfortunately the actual traffic load is generally not going to be split 50-50 between the individual VLANs. So we're going to still end up in underutilized links that are going from the access layer to the distribution layer. Okay, a second solution for this is to run the open standards equivalent version of HSRP, which is called the Virtual Router Redundancy Protocol, or VRRP. Okay, as I mentioned, it is an open standard. It's defined in RFC 5798, the Virtual Router Redundancy Protocol version 3. Okay, in this case, the switches likewise agree on a virtual IP address and a virtual MAC address of the default gateway, and the end stations ARP for that default gateway, and they're going to be returned back a virtual MAC address. Okay, still the limitation that we run into is that only one of the distribution switches is going to be the active forwarder. Okay, specifically we call one of the switches the master gateway and we call the other one the backup gateway, but the result is that the redundant uplinks from the access layer to the distribution layer might be underutilized because we only have one active forwarder. Okay, we run this in what we call an active standby type design. Okay, likewise, we could potentially do load balancing with VRRP by doing multiple copies of the protocol, where we could have one default gateway for the even VLANs, another default gateway for the odd VLANs. But again, unfortunately, in most real-world solutions, the split of traffic is not going to be a 50-50 share between the VLANs and the services that they're running on those particular virtual LANs. Okay, a third potential solution for this is to run the Gateway Load Balancing Protocol, or GLBP, which does allow for active-active forwarding from both distribution switches at the same time. So the idea here is that the switches agree on a single virtual IP address, but there's going to be multiple virtual MAC addresses that represent the default gateway. So the end stations are going to ARP for the default gateway, and they're going to be returned with one of the virtual MAC addresses that is representing the distribution switch. So load balancing is going to occur because some end stations are going to point to one MAC address which relates to one of the distribution switches. Others are going to point to a second MAC address which is going to point to the second distribution switch. Okay, it's still not the greatest of the solutions because, again, we don't have a 50-50 split in the load between the individual host traffic, and we're not going to be load balancing per flow. We only are going to be load balancing per host. Okay, now in an alternate design called Layer 3 Access, in a Layer 3 Access design, we're moving the routed edge from, we're moving this southbound from the distribution layer to the access layer. Okay, so in the Layer 2 design, we would be running Layer 2 up to the distribution. So Layer 2 is going to be going southbound from the distribution switches to the access layer. And then we're going to be running Layer 3 routing as we go upstream from the distribution layer to the core layer. Now in the routed access mode, we're going to be pushing the Layer 3 boundary down all the way to the access layer, where we're going to be running layer 2 switching southbound to the access devices, and we're going to be running layer 3 northbound as we go upstream towards the distribution switches, and then likewise we're going to be running layer 3 routing as we go towards the core. So the difference here is that these interconnections of links are going to be running layer 3 IP routing as opposed to running layer 2 switching, which means that they're not going to be subject to spanning tree protocol. So this is going to be the main advantage of layer 3 access, is that the spanning tree protocol is going to be limited down to the access layer. Okay, so the access to the distribution layer 2 trunks are going to be replaced with layer 3 routed links, and the access layer now needs to participate in routing protocols. So either OSPF or EIGRP, for example, are typical design options that we would use in our campus environment. Okay, this also means that the default gateway moves down one layer. So the access layer switches are going to be the default gateways for the end hosts, which is going to remove the need for the first hop redundancy protocols, because the end stations are typically only single home to an access switch. Okay, if we had multiple connections from the end host to the access switch, that would be a different story, that we would run first hop redundancy protocols at the access layer. But in the vast majority of cases, we only have single connectivity that's going from the access device to the access switch. Okay, also, as I mentioned, in the layer 3 access design, this removes the need for spanning tree protocol. So there is no longer going to be any blocked links that go from the access layer to the distribution layer, and load balancing is now going to occur based on layer 3 routing. Okay, so the big advantage of this is that load balancing can now occur per flow. So an individual transaction like web browsing would have multiple flows. As we're doing HTTP GETs going to the server, we could be load balancing those between the multiple links that are going from the access layer up to the distribution layer. Okay, the big advantage of this is that we're increasing the uplink bandwidth utilization, and we're not doing active standby forwarding like we would be doing in spanning tree. Okay, this also makes the network easier to troubleshoot now that spanning tree is going to be removed, and it also is going to give us faster convergence now that spanning tree is removed, because convergence is going to be a function of either OSPF or EIGRP, whatever our routed protocol is, and we can tune them for sub-second convergence, assuming we have the network configured properly. Okay, the potential limitation, though, of the layer 3 access design is that we cannot span VLANs between multiple access switches, because we're not running layer 2 trunk links as we go from the access layer up to the distribution layer. Okay, now the best of both worlds would be if we were using what would be considered a simplified campus design, where we're using switch clustering techniques such as the virtual switching system, or VSS, or Stackwise at the access layer, where multiple switches are going to act as one. Okay, this is going to remove the requirement for our first hop redundancy protocols, or our FHRPs. So we don't need HSRP, VRRP, or GLBP when we're running the virtual switching system, because we're going to have one logical address, one logical IP address, and one logical MAC address that's going to represent multiple physical chassis that exist in the physical topology. Okay, it's also going to reduce the need for spanning tree. So the access layer is going to be using port channels or ether channels to connect to the distribution layer, where spanning tree would still be used as a fallback in the case of system failures. Okay, so here we have an example of the physical connectivity versus the logical connectivity of the VSS. So the VSS is going to consist of a pair of switches, a pair of distribution switches that are multi-home down to the access layer, and in the access layer we're running a port channel or an ether channel that's going northbound to the VSS. Now, from a logical point of view, the southbound access switch is going to think that the upstream device is just one physical switch, which means that if we lose an individual link or we lose an entire node, so if the entire switch goes down, the convergence is going to be based on the port channel load balancing mechanism. So we would just remove a member interface from the port channel channel, and then we would be able to continue forwarding our traffic northbound up to the distribution layer. Okay, so in the simplified campus design, this is going to increase our uplink bandwidth utilization. So traffic is going to be load balanced per flow from the access layer to the distribution layer across the port channel, based on the port channel load balancing mechanism, and it's also going to reduce convergence time. So the port channels offer a sub-second reconvergence on the failure of either a member interface or a failure of the node in the VSS. Okay, another advantage of the simplified campus design is that we can distribute our VLANs between multiple access switches without blocked links, because the port channels are going to be layer 2 interfaces that are going from the access layer up to the distribution layer. Okay, last but not least, this is also going to simplify our management, because the cluster of switches is going to be managed as if they were one single logical device.